Okay, let's get started. In this last lecture, we are going to talk about mixed integer programming solvers. And there won't be much math in this lecture, so you can sit back and relax. It just tells you how to use the softwares. Let's see if I can do full screen mode. Oh yeah, I should share my screen on Zoom. Okay. So, yeah. So to start with, just a little bit history of mixed integer programming solvers. I would say one of the first commercial solvers in this space is called Cplex. Cplex predates Groovy, and it was originally written in the C programming language back in the 80s by Robert Bixby. And he formed a company called Cplex Optimization Inc. And later on, it was acquired by a company called iLog in 1997. And later it was acquired by IBM. So currently Cplex is owned by IBM. And then in 2008, these three gentlemen, Zhong Haogu, Edward Rothberg, and Robert Bixby, they were working for Cplex, but then they left Cplex and founded a company called Groovy, right? So you see Groovy is named after the three of their last names. And if you check Groovy and Cplex, the design are very similar. And so far, I would say, according to the Mittelman benchmark, Groovy is the best performing MILP solver. Cplex is no longer in the benchmark anymore because they don't want to be in the benchmark. And then Groovy can now solve non-convex MIQCQPs. It's not restricted to MILP problems. And starting with Groovy version 11, it can solve very simple MILP problem without those factorization schemes. Okay, so let's talk a little bit about what's inside the box of the solver. Because nowadays, when you use the solver, perhaps you just treat it as a black box, right? You write a Python model, then you call a solver to solve the model, right? But from the theory we have taught you so far, you should probably be able to understand part of what's inside the box of the solver. But there are a lot of other techniques we haven't talked about in this class. So basically, I would say the main capabilities of a branch and cut solver include things like pre-processing, cutting planes, heuristics, of course, a branch and bound, and some callbacks. And if you look at Cplex and Groovy's document, there are hundreds of parameters you can change before you solve an MILP. But by default, it will just use the, it believes to be the best parameter. Okay. So let's talk a little bit about pre-processing. If you run a piece of code, you probably will recognize that you start with a huge number of variables, and then it tells you that pre-process help you reduce the number of variables to a smaller number. It can do things like remove a bunch of variables and constraints that are redundant. It can tighten the variable bounds and so forth. And there are ways you can control, how Groovy use presolve. So if you click on this link here, I say, so this is a parameter called a presolve, right? Let's see if I can zoom in. Is the font large enough? Okay, yeah. But as you can see, by default, it takes a value of -1, right? The -1 corresponds to automatic setting. Other options are, if you set this parameter to 0, then it will turn off the presolve. 1 is conservative, 2 is aggressive. So then you can change the aggressiveness of using presolve in Groovy by changing this parameter. But if you don't want to bother doing that, then just use the default value. This is pre-processing. Then it has different types of cutting planes inside the box. This is what I took from the Cplex user documentation. So those are all the cutting planes implemented in a commercial solver. We've talked about, perhaps you still remember Gomery fractional cuts. We did show you how to derive the Gomery fractional cuts, but it's just one of the let's say there are around, let's say 15 cutting planes implemented in the solver. And the solver is very well fine-tuned to decide which cutting planes to add. If you are curious about those cutting planes, you can read some textbooks on integer programming to learn a little bit more about that. And similarly to pre-solve, Cplex and Groovy can also control how aggressive you want to generate the cutting plane, right? So if you click on this link here, there's the option called cuts. Default is automatic. Let's say again, 0 is to shut off the cutting plane generation. 1 is to do moderate cut generation. 2 for aggressive. 3 for very aggressive. Right, so you can change the level it generates the cutting planes. And of course, there are some trade-offs in how aggressive you want to add a cutting plane, right? If you add more cutting planes, the relaxation will be better, right? The goal of the cutting planes is to help you tighten the LP relaxation. But that means that you will require fewer branch and bound nodes to converge to the optimal solution. But the downside is that each of the node is much more expensive to solve as you add more cutting planes. So there are some trade-offs here for some problems. Maybe you want to be more aggressive in adding the cuts. Yeah, and then heuristics. So we will talk a little bit about heuristics in this lecture because we never talk about heuristics before, right? So if you are solving a minimization problems, the LP relaxation give you the lower bound, and then you keep branching, you can improve the lower bound, right? But the upper bound is obtained by the heuristics. So there are different types of heuristics the MIP solver used. I would say the major, let's say the market value of the commercial solver are actually in the heuristics. It used all sorts of heuristics. They did a bunch of experiments on, how do you get good feasible solution? And then they did a lot of experiments on what are the good heuristics of selecting cutting planes. That's actually their commercial secret. You don't know, when they are using the heuristic and so forth. And similarly, I can click on this again. So for heuristic, there is actually a continuous value you can choose on how much time you want to spend on heuristics, right? So here, by default, they aim to spend 5% of the runtime on heuristics. If you change it to 1, you will spend 100% of the time on heuristics. Okay, so this is a parameter you can tune. I guess Groovy believes 5% is a good time. Okay. Yeah, so let's talk a little bit about what are the commonly used heuristics in a MIP solver. The most naive approach is called the neighborhood search. Okay, so let's denote X star be a solution to a given LP relaxation or a given node relaxation in a branch and bound. So if you have some integer variables, the neighborhood search means that you can round up and round down this integer variable, right? For example, this number is 3.6, then you let this number to be between 3 and 4. Right? So you reduce the range of the integer variables, and you solve a sub-mixed integer linear programming in the neighborhood of this LP solution. Right? So this only applies to general integer variables. But for binary variables, you can just do a simple rounding, right? Let's say all the variables are binary. Let's round all the binary variables and then solve the rest of the linear programming problem that hopefully give you a feasible solution. Okay, and if you are doing the sub-MIP search, usually it is truncated by a limiting number of nodes. You don't want to spend too much time on the heuristic, and there is it's not necessary to solve a sub-MIP to optimality. You just want to find a good feasible solution. And another slightly more complicated heuristic is called local branching. Okay, let's talk about this real quick. So suppose we have a feasible solution, X hat, right? So the so-called reference solution is this feasible X hat. The X hat can be obtained from a heuristic, or you just happen to get an integer feasible solution at that node, right? So let's denote the set S as all the indices where the X hat equals to 1. For among all the binary variables, some of them equal to 1, some of them equal to 0. So the S set S is denoting the binary variable that equals to 1 at this particular feasible solution. Then we define a neighborhood of this X hat, meaning that I want to consider a neighborhood such that the solution you consider compared with X hat only differs in K, at most differs in K variables, right? So in total, let's say maybe you have 100 binary variables, but you say all the solution I consider can only differ from X hat in 5 of the binary variables. All the rest are the same. So this delta set, X hat set, is creating a K neighborhood of X hat, right? So remember, S is a set of binary variable that equals to 1. Okay, so if all the binary variables still equals to 1, then this term is 0, right? And this set I/S means the set of variables that equal to 0. So if you plug in the original X hat, the distance is 0 here, right? Basically, this equation calculate the number of binary variables that changes from X hat to X, right? So it has to be less than or equal to K. So this constraint is so-called a local branching constraint, right? It restrict the solution to the neighborhood of X hat. And then you can solve this sub-MIP problem relatively fast because you are searching around a smaller neighborhood. Okay. So you can use this type of local branching constraint in your branch and bound algorithm as well, right? So if you branch on the left, you say the distance has to be less than or equal to K, then the right node can be, the distance are greater than or equal to K plus 1. So you can use this local branching constraint as a branching rule as well in a branch and bound method. But you can just assume when we use that, you just restrict to a smaller neighborhood and say doing a local search. Let's say if we can find a better solution. Yes.
That's the value of K. Or what is the value of K?
Yeah, so it's a hyperparameter. So you can tune the size of the K to see which K performs better. Yeah. But generally, K is much smaller than the total number of binary variables. Yeah. Any other questions here? Yeah, so the other heuristic is so-called relaxation-induced neighborhood search, right? So it's similar to the neighborhood search, but it takes into account both the incumbent solution. So X bar is a feasible solution found so far, and X tilde is a solution of the continuous relaxation, like the LP relaxation. So basically, X tilde gives you a lower bound, X bar gives you an upper bound, right? If you are minimizing. The feasible solution is an upper bound, the relaxation gives you a lower bound, right? And then we compare all the binary variables in X bar and X tilde. And we will fix all the binary variables that are the same among X bar and X tilde, okay? And then the associated MILP is solved by using the MILP solver, okay? So in case the incumbent solution is improved, X bar can be updated in the rest of the tree. Okay, so let's show the formulation real quick, then you will understand it. So let's say your original problem is C transpose X, then the AX less than or equal to B are the linear constraint, then X is a mixed integer here. But then we will fix all the variables such that this variable is the same in X tilde and X hat, right? So some of the binary variables may be the same in the relaxation solution and the feasible solution, right? So if they are the same, intuitively, those variables can be fixed, right? One gives you an upper bound, one gives you a lower bound. If they happen to be the same, then you can fix those and then just solve for the rest of the variables. Right. And with that, if they have a lot of overlap, you are basically fixing a large number of variables here and solve a smaller MILP problem. Okay. And the other approach is so-called solution polishing. The intuition is that if you have a number of good feasible solutions, then you can kind of combine those good feasible solutions to generate other good feasible solution. This is in a similar idea to genetic algorithm. Perhaps people have heard about genetic algorithm. It's just a heuristic to solve combinatorial optimization problem. But genetic algorithm doesn't give you the global optimality guarantee. Right? So you can the usually used operation in genetic algorithm is mutating and combining. You can mutate this the good solution you got so far, and then you combine those solutions to get a new solution and so forth. This is like how genes mutate and then they combine with each other, right? They draw the intuition from how genes evolved, right? That's why it's called the genetic algorithm. But for MILP problem, as you can see, this paper was developed by one of the founders of Groovy, Robert, right? So that also requires solving some sub-MIPs, even if you combine with genetic algorithm. Okay. Yeah, and then another heuristic is called the feasibility pump. So let's suppose we start with a solution X naught. So here the P denotes the polyhedral constraints or all the linear constraints in the problem, right? So finding a feasible solution to a linear programming problem is relatively easy. You just solve a linear programming problem and maybe you find a solution to the LP relaxation. But if you start with a solution that satisfies the linear constraints, it doesn't satisfy the integrality constraints, right? So what you can do is you round this X node to get a X hat node, right? And now the X hat node will satisfy the binary constraints, but it may not satisfy the linear constraints anymore, right? So that now you look for a point to project this X hat to the closest point in this polyhedral. Right? Okay, so first of all, you have a point that is satisfy the linear constraints, but not satisfying the binary constraints. But if you round all the fractional binary variables, it will satisfy the binary constraints, right? Once you round the binary variable, it may not satisfy the linear constraints again, right? So you can solve a optimization problem to minimize the distance of X from X hat, and also X satisfy the linear constraints, okay? And then if you choose this properly, this is easily solvable, right? For example, you can minimize the two norm distance, right? Then it is a quadratic problem with linear constraints. Yeah, but then after you solve this projection problem, it doesn't satisfy the integrality constraint anymore. So you run again and you keep repeating between these two steps, right? So the idea of feasibility pump is kind of like an alternating projection algorithm. You first project to the linear constraint set, then you project to the integrality constraint set by rounding, right? If you are lucky, then you will converge to a point that satisfies both the integrality constraint and the linear constraints. But this convergence is not guaranteed, actually. The alternating projection algorithm only converge if the two sets are convex. So this result actually predates optimization. When people are considering how do we project a point to the intersection of two convex sets, right? They are doing this alternating projection. But here we are projecting to the polyhedral set, which is a convex set, but the integrality set is not a convex set, right? When you are doing the rounding. So the feasibility pump doesn't converge. It doesn't have theoretical guarantee of convergence, but in practice it works. Okay, yeah. But basically you are doing it in a complementary way. In one iteration, you are going to satisfy the linear constraint. In one iteration, you satisfy the integrality constraints. Okay. Any questions so far? Yeah, so then let's talk about another property. So that's everything we want to talk about for heuristics. And there's another option which can be very effective when you solve real-world applications, especially, let's say, scheduling problem. You are going to use this a lot, okay? So this is something called branching priority. What I mean is that if you have an MILP problem and you give it to Groovy, then Groovy will use its own branching rules, right? Things like pseudo-cost branching, right? But it won't be aware of the structure of your problem. Right? perhaps for your problem, based on your knowledge of the problem, if you branch on some of the variables first, then all the other variables will be fixed, right? Like in scheduling problem, you first assign the jobs to the machines and you decide what are the sequence of those jobs on this particular machine. So I would branch on the variables that specify the assignment first before you specify the sequence. Okay, that's one of the intuition why you are doing branching priority. So if you want to specify this structure, you can change this set branching priority setting. Okay, so it says the value of this attribute is used as a primary criteria for selecting a fractional variable for branching during the MIP search. Okay, so you can specify the the value of those branching priority value. It comes as an integer value. So variables with larger value always takes priority over those with smaller values, right? So let's say there are two sets of the variables. One is assignment of job to machines. The other sets of binary variable are the sequencing variables within each machine, right? So you can assign a number. Let's say we assign number 2 to the assignment binary variables, and they assign number 1 to the sequencing binary variables, right? Then Groovy is aware that you have to first branch on the assignment variable before it starts branching on the sequencing variable. In other application, maybe you have even more hierarchy of branching priority. So this can be very effective if you know a very good structure of your problem and change the branching priority. Okay. Yeah, so the other thing to keep in mind is so-called solution pool. In some of the application, usually you may wonder, can I get more solutions? Right? Even though some of the other solution may not be optimal, but you are curious to know whether there are other close to optimal solutions. Right? In some of the applications, you may want to do that. So by default, Groovy will only give you the solution it found along the branch and bound process. In some of the nodes, it can be happen that it happened to encounter a solution, it will save that, but it won't give you additional solutions that are not necessary. Yeah, for example, let's say if you want to find all the binary feasible solutions to a pure binary program, right? How do you do that? So there are some settings you can take a look. Like this is called pool search mode. The default value is 0 and the maximum value is 2. Okay, so here, as you can see, select different modes for exploring the MIP search tree. With the default value, the MIP solver tries to find an optimal solution to the model, and it keeps other solutions found along the way, right? But those are incidental. In some of the nodes, you may happen to find a solution, it will save that, but it will not kind of intentionally find additional solutions for you. But then if you, let's say by setting to non-default value, MIP search will continue after the optimal solution. Yeah, so if you change this setting to non-default value, it will intentionally continue finding additional high quality solutions for you. Okay. So the MIP solver will try to find n solutions where n is determined by the value of pool solutions parameter. Okay, for example, if you want to know 100 optimal solutions, close to optimal solution to this problem, then you can set this pool solutions parameter to 100. Okay, and then that will give you more feasible solutions. Right? Of course, to find more feasible solution, you need to do more branch and bound. Okay. Questions here? Yes.
I have a question.
Yeah, go ahead.
So like if you're using heuristics, how does it guarantee global?
Oh, so it doesn't guarantee, it's just part of the branch and bound solver. Right? So by default, you are doing branch and cut. Right? In a solver, you are doing branch and bound, adding cutting planes to tighten the bound. But you also want to find good solution, right? Such that you can fathom some of the nodes if they are, you can fathom them by optimality. So all those things are happening together in a branch and bound solver. Yeah. Other questions? Yeah, I remember one of you asked me about this thing called multi-objective. This is very simple to do. So let's say if you have a problem where you want to optimize multiple objectives. Just to give an example, let's say if you have an energy system planning problem, you want to minimize the total cost of building those energy systems, right? You want to minimize the cost of building a chemical plant. But the other objective is that you want to minimize the CO2 emission of this chemical plant as well, right? And these two objectives are not in the same unit, right? The cost of the chemical plant is in dollars, right? And then the cost of the CO2 emission is in, let's say, tons of CO2 per year you are going to emit, right? So those two are two conflicting objectives. You want to minimize these two objectives at the same time. How do you implement that in an optimization problem? Actually, you cannot just optimize these two objectives at the same time, right? Of course, it's very easy to imagine that you cannot say the minimum cost chemical plant is a minimum emission chemical plant. It's usually the other way around, right? Yeah, so the way you do it is take a convex combination of your n objective, right? So here, n can be any arbitrary number. So you can pick different weights on different objectives, right? So let's say if you care more about cost, then you put higher weight on cost. If you care more about CO2 emissions, you put a larger lambda number on the CO2 emissions. So by changing the values of lambda, you would obtain something called, not Pareto font, it's Pareto front. Yeah, so you obtain the Pareto front of your multi-objective optimization problem. So what does Pareto front mean? That means you are at a point where you cannot optimize any objective without sacrificing the others, right? So you are kind of at the boundary of your multi-objective problem, right? If let's say if you can still minimize the cost a little bit, that must mean you have to increase your CO2 emission, right? So that's called the Pareto front. So how to choose those lambda value in practice? One of the ways is to think about the physics of your problem, right? Let's say the CO2 emission and the cost of the chemical plant are in different units. You can assume that, for example, in the future, people will be charged with a carbon tax, right? So if you emit 1 ton of CO2, let's say for the sake of the argument, you will be charged $10, right? So then you can just multiply the CO2 emission by $10. That number is decided by you, right? You don't know what will be the perfect number to use. It's more about the preference of the optimizer, how he or she wants to pick the weights lambda here. Okay. And then you can do multi-objective easily in Groovy. It probably will offer you some ways of defining multiple objectives. I'm not going to the details. Okay, so besides this type of multiple objective called Pareto front, there is something else called hierarchical multi-objective or lexicographical multi-objective. Okay, so that means if you have multiple, let's use the same example, cost and CO2 emission, right? You can take a weighted sum of these two objectives that gives you the Pareto front, right? But let's say I only care about the cost more than the CO2 emissions, right? So what you will do is that you first minimize the cost under the condition that you are going to achieve minimum cost in the chemical plant. If you still have some flexibility, let's say there are multiple chemical plants that give you the same cost. And then you are going to choose the one with the minimum CO2 emission. So there is a hierarchy in your two objectives, right? You first optimize the cost that perhaps will give you a non-unique solution if you are lucky, right? And then among those alternatives that gives you the minimum cost, choose the one that gives you the minimum CO2 emission, right? It's like in the bi-level optimization problem, your lower level may have alternative solutions, and then you pick the one that is optimistic but for the leader, right? This is a similar thing. I didn't talk about hierarchical, but Groovy can also do that for you. Yeah, so I want to talk about linear programming algorithm a little bit. So nowadays, a lot of people believe that linear programming is a solved problem. It can be solved pretty fast for large scale problem. But I disagree with that perspective. For large scale linear programs, it's still not so easy to solve. If you have a linear program with a billion variables and you try to solve it with Groovy, it can be super slow. So yeah, so what my point is that linear programming algorithm do matter when you have a super large scale problem. So here in Groovy, there are, I would say, 4 different methods for solving linear programs. One is primal simplex, second is dual simplex. Then we have, people probably will remember barrier algorithm. Remember we talk about the log barrier function in interior point methods. So it also has barrier algorithm with and without crossover. So what does crossover mean here? When you use simplex algorithm, it is guaranteed that your solution is a basic feasible solution or an extreme point of your polyhedral set, right? But in interior point method, there's no guarantee that you will end up with an extreme point, right? So we have a homework question where we asked you to try solving a given LP using simplex and then change the method, solve it with barrier again. You probably will recognize when you solve it with barrier, the solution looks a little bit more ugly than the primal simplex because a lot of solutions give you values like 10 raised to the power of -8 instead of 0. Right. So that's a reason. The reason is because in barrier algorithm, it just gives you a feasible, optimal solution, but it doesn't have to be an extreme point. If the problem is degenerate, there are multiple, optimal solutions, then it may end up on a face of the polyhedral instead of on extreme points. So crossover means after barrier algorithm terminates, it will try to push the solution to an extreme point. Okay, that's what crossover means. And sometimes crossover can be even slower than the barrier algorithm itself, right? So meaning that in barrier algorithm, getting a solution is fast, but getting an extreme point solution can be even slower than getting the optimal solution, okay? Now you can change this algorithm using this called methods. Okay, so I will read it real quick. So -1, it means automatic, right? Groovy might have some very good classifier on which algorithm to use. So if you choose 0, then it will use primal simplex. Choose 1, it use dual simplex. 2, it means barrier. 3 means concurrent. Concurrent means that, if you have a multiprocessor computer, it will try all the 3 algorithms at the same time. And it will, whichever process terminates first, then it will return you the solution. Okay. But how do you change crossover if you use barrier algorithm? There is another parameter called crossover here, right? So if you use 0, then those things are disabled. And then if you change different parameters, it will give you different settings of they have 2 different phases. One is a primal push. The primal variables are pushed to the bounds, and there is a dual push where the dual variables are pushed to the bounds, right? And then there's a cleanup phase where simplex is used to remove the primal and dual feasibilities, right? So if you want to get an extreme point solution, simplex has to be used at the end to recover an extreme point solution for you. Okay, and this process can be quite slow. You have a question?
Yeah, what's the incentive of doing like the barrier algorithm with crossover when the simplex method just gets you the extreme base?
Yeah, because it can be faster than the simplex algorithm.
Okay.
Right. So in theoretically speaking, simplex algorithm is not a polynomial algorithm. It can run exponentially, right? So if you consider the number of extreme points in a polyhedral, right, there can be n choose m number of extreme points in a in a polyhedral set. And in the worst case simplex algorithm, we may have to enumerate all those combinatorial number of extreme points. So in practice, usually barrier algorithm is faster than simplex algorithm. If you let's say if you disable crossover, you just want to solve an LP and get the optimal objective value, right? Then you definitely choose barrier without crossover. This is not the default option in Groovy, right? So keep in mind that when you solve LPs where you don't care about whether it's an extreme point or not, you should change the setting of Groovy to use barrier without crossover, right? It will be much faster than simplex for very large scale problem. If you have a 1 million variable LP, then barrier without crossover will run much faster than simplex. Okay. But the other thing is that if you think about that, maybe for most of the LP applications, we would just use barrier, right? Why do we care about the solution is an extreme point or not? Right? We do want a clean solution, but it doesn't seem to be so necessary. Right? So the reason why simplex is so widely used is mainly for solving mixed integer linear programming problem. Why that is the case? Because remember, when we talk about primal simplex and dual simplex, the difference is that in primal simplex, once you change the variable bounds, then the solution is no longer feasible, right? But if you use dual simplex, right? Think about in branching, what you did, you just changed the variable bounds in branch and bound, right? So the feasible region of the primal problem got changed after you branch on some of the variables, but the feasible region of the dual doesn't change, right? When you do branch and bound, okay. So that's why dual simplex is amenable to warm start when you do branch and bound, right? You can start with the dual feasible solution after you branch. So that's why when you observe in a branch and bound method, the root node LP takes a lot of time to solve because you need to get an extreme point solution in the root node relaxation. But after it starts branching, it surprisingly goes very fast, right? The reason is that you are not solving the linear programs from scratch when you start branching. You are going to warm start the node relaxation with a dual feasible solution from the root, from the parent node, right? That's why Groovy can be very fast in enumerating the nodes, okay? So this is the reason why you need an extreme point, because to warm start dual simplex, you need a dual extreme point to warm start dual simplex. Okay, that's just a little bit what's happening underneath the hood, right? So that you don't treat this as entirely a black box. Okay. Is there any question here? The logic is a little bit more complicated than the previous slide. Yeah.
Crossover.
Yeah.
The Groovy solver knows where to round up the number and just try to.
Yeah, I think so. I don't know how exactly the crossover works, but maybe my guess is that it will try to round the number, then it somehow will give you a good solution to warm start the simplex, but still it has to run some iteration of simplex. Yeah. Any other questions? No. Yeah, and then finally, let's talk a little bit about parallel computing. As you can imagine, branch and bound can be easily parallelized, right? You are basically doing a tree search and all the nodes can be parallelized. You just need to synchronize the bounds you get from each of the nodes with some sort of master process. So if you have a multiprocessor computer or a server, you can change the number of threads will be used. So I think now by today, by default, it will use all the processors you have on your server. Yeah, so it generally uses, if the default value, it generally use as many threads as there are virtual processors. So if you are running Groovy on a server, if you have, let's say, 100 processors, all the 100 processors will be used. So then you have to be a little bit careful, right? If your lab mates are also running some code, you don't want to use all the threads on the server. Right. So if you are running something on a server, then you should probably set it to a smaller value than the total number of processors on a server. Okay, such that you don't conflict with your lab mates processes, right? Yeah. Then let's talk a little bit about the solver APIs, right? All the MIP solvers, mostly them are written in C. Maybe some of them are implemented in C++, right? Because those compiling language are very fast to run, right? The interpretable language like Python, they are very slow, right? You will never write a solver in Python. All the lower level linear algebra and stuff that's are usually written in C or in Fortran. But then in order to use this solver that is written in C, people have developed APIs, right? All the solver vendors, they generally have APIs in C, C++, Java, Python, MATLAB, and R, right? Now, most people use things like Python and MATLAB or Julia as well, right? Very few people will write an optimization model in C and C++. Right? You'll probably need 2 more years to graduate if you write your code in C or C++. Yeah, but how does Pyomo work? I recall that all those solvers are created by different software vendors. All their APIs are different, right? Those APIs are solver dependent, right? But Pyomo is kind of like a solver independent algebraic modeling language, right? So in order to talk to different solvers, Pyomo must have implemented something such that it can communicate seamlessly with different solvers, right? And so does Julia. If you want to use Julia and use Jump, it can talk to different solvers using different solver APIs. And there are different ways let's say Pyomo or Jump can talk to different solvers. One of the ways is to write the model in a so-called .lp file. If you have an MIP model, there is a ubiquitous format for all the optimization solvers in the format of .lp file. And you can save that .lp file to your hard drive and then use that solvers API to read that LP file again, right? So I believe that's the default version when you use Pyomo. Okay, but there is another way to communicate with the solver. They are called Pyomo persistent solver. So this is not through communicating through LP file. The way it works is that it will communicate with solver through their own Python API. Okay, so Pyomo has a Python API. You can write a Python model using Groovy's Python API, right? Well, you can write Python code in Pyomo. Okay, but then there must be some connection between your Pyomo Python code and the Groovy Python API model. So there's a one-to-one mapping between these two models that Pyomo creates for you. Okay, so if you are curious about how this was implemented, you can check the code on GitHub. Right, this is a Pyomo repo. Again, so when you are working on open source projects, the best documentation for any repo is the code itself, right? Maybe the developers are too lazy, they didn't update their documentation, but the code is the best documentation. You should learn how to read their code. So the way it works is as follows. So okay, so let's say, yeah. So there are some objects within this class that are quite important, which is this solver constraint to Pyomo constraint map, right? By solver constraint, it means the constraint of in a Groovy Python APIs model, right? So there are two models here. One is called solver model. So this is a model created based on the Groovy Python API, right? And there's another object called Pyomo model. This is a Pyomo model you write, right? But as I said, you need to create a mapping between the model you wrote in Pyomo and the solver model created based on the solver's Python API. But how do you map those these two models, right? You need a mapping of variables and you need a mapping of constraints, right? So here, what they did, there is a dictionary where you can map the solver constraint to Pyomo constraint. I believe if you scroll down a little bit, there must be a mapping between solver. Yes, we see there is a solver var to Pyomo var map, which is a mapping between the solver variable and the Palomo variable. Okay. So why I'm talking about this, if you don't care about the more sophisticated functionalities of the Python API, you don't need to know this. But sometimes you need to implement some additional functions, because Palomo doesn't provide you all the capabilities of the solver, right? But the Python API of the solver may provide you all the capabilities. So in order to incorporate those capabilities into the Palomo, you may need to implement some of your functions here. Okay, I've done one of this stuff before, because the Palomo developers may not implemented all the wrappers for the Python API. Okay. So just want to talk briefly about that. If you want to implement that, then you can go in more detail into this. I say yes.
Is it like only compatible with
Yeah, so there is a Groovy persistent. Yeah, that's a good point. I should go back. If you go above this folder, so that's all the let's say wrappers of Palomo with other solvers. For example, you can find the cplex.py as well, but not all of those have a persistent solver, right? So let's say Groovy has a persistent solver. Let's say if cplex has a persistent solver. Yeah, so cplex also has a persistent solver. But you say this piece of code is very short. They didn't implement everything you can do with cplex. If you want to use something in addition to what a Palomo developer has developed, you need to implement your own functions. Okay. Yes.
I'm sorry, what do you mean by persistent solver?
Yeah, so persistent solver means that you are using the Python API to call that solver. That is what they call persistent solver, because you can communicate with the solver seamlessly in some sense, right? It will become more clear if I go to the next slide with the callbacks. Okay. Yeah. Yeah, so now I'm going to talk about some capabilities called callbacks. I briefly mentioned about this before in the lectures of like Bender's decomposition and single tree alter approximation. So the idea of callbacks is that you want to interfere the branch and bound process. So nowadays, when you guys have a model in Palomo, you just solve it with a solver, then that's it, right? You cannot interfere the branch and bound process. So supposedly you want to interfere with the branch and bound process, for example, adding some lazy constraints. So what are the lazy constraints? That means when the full set of constraints are too large to include in the initial formulation. Remember in the traveling salesman problem, we talk about the subtour elimination constraints, right? You cannot have a subset of a city where you have a tour within a subset of the cities, right? And that type of constraint can be exponentially large, right? You basically have n choose number of n-1/2, something like that, number of constraints. And you don't want to add all those constraints, and most of those constraints are not useful, right? And similarly, in things like alter approximation, you are not going to add all the OA cuts, or in Bender's decomposition, you are not adding all those cuts at the beginning, right? So you want to dynamically add those cuts while you are doing the branch and bound. Okay, now the idea is that when the MIP solver reaches a new solution, it can reach a solution at any node in a branch and bound tree, right? And remember that you haven't added all the constraints at the beginning. Right? Now you can check if your feasible solution violates any of the constraints, you are going to add this constraint back, right? And typically this is called so-called cut separation process. Remember, you always want to find the most violated cut. Right? That is so-called cut separation problem. This problem can be pretty hard for some of the problem like traveling salesman. How do you separate the most violated cut in the subtour elimination constraints, right? Because there are exponential number of them. You don't want to evaluate exponential number of them all the time, right? So that's one of the problems the combinatorial optimization people have to deal with. Yeah. And lazy callbacks are more flexible than lazy constraint. Maybe you want to implement a tailored function for your problem. Meaning that once you encounter a feasible solution, then it will automatically execute a piece of code you have implemented before. Maybe give an example, let's say the single tree outer approximation algorithm. Just to refresh your memory, how does that work? That is, if you have an MIP master problem, initially you are starting with no outer approximation cuts, right? But then at some of the nodes, you may find an integer feasible solution to the MIP. Now what you will do is that you will solve the NLP and then solve the NLP to optimality to find the optimal continuous variables and then add OA cuts back to the branch and bound tree. That's what you're doing single tree outer approximation, right? So in that case, in the callback function, what you will include is that you will have a function to solve an NLP in that problem, right? It's not just adding a constraint. You have to first solve an NLP, then you add a constraint, right? And similarly, in single tree Bender's decomposition implementation, you have to solve all the Bender subproblems after you encounter a feasible solution. After all those subproblems are solved, you add Bender's class to the single tree. Okay, yeah. So this may sound too abstract. Let's go to a small example in Stack Overflow. There is someone who posted an answer here. I'm not sure if the code still runs, but you will get the idea by looking at the code. Okay. So this what they posted here is a piece of code to add, let's say, add a callback to Groovy, right? So first of all, here's a very simple Pyomo model they have implemented, okay? And then they implemented a function called add cut, right? So let's not worry about this function now. Okay, but then it tries to use this function. So remember that here's what persistent solver comes into the play. In order to use the callback functions, you have to use the persistent solver. Okay, so remember that in the callback function, you are interfering the branch and bound process, right? That's why you need to use a Python API. If you do the other way around, let's say you save this optimization to a .lp file, then you load that again using the C API. You no longer have the control over that optimization model anymore if you do it in the default way. So you need to have some dynamic connection with the optimization model while it is running, right? So that's why we have to use a persistent. You can interpret persistent as you have a persistent connection with the optimization model as the algorithm runs, right? Yeah, and then you have to set some parameter. Let's say you want to add a daily constraint. Okay, so this callback function is the most important thing we need to take a closer look. But first of all, you don't need to care about those arguments for now, right? So let's first talk about this CB where thing. So this CB where object will determine at which condition will this callback function be activated, right? So remember that in the subtree elimination constraint, I would only want to add a cut when I find a feasible solution to the MLP, right? If you are solving a relaxation, you don't add those cuts. So that's why it says when the GRB is a Groovy object, when it has find a MIP solution, then you will check, you will go to the additional code here, right? So you will only care about adding cuts when the MIP solver has find a feasible solution to the MLP. Then you will add the subtree elimination cuts, right? So that's why it first check whether you are at a MIP solution or not. Okay, so if you are at a MIP solution, you can get the solution of those variables, right? And if you check the values of those variables, if they satisfy those conditions, then you add a cut to the problem, right? So imagine if you are at the subtree elimination constraint. First of all, you check whether I get a MIP solution or not, right? And then you, let's say for a very naive argument, you go over all the subtree elimination constraints identify the most violated one, you are going to add that back to the to the branch and bound tree, right? So you will check some values related to the MIP solution, then add those cutting planes, right? So now you have defined your callback function here. Any questions related to the callback function? Or maybe let's say if you are implementing an outer approximation algorithm, what you will do is that when you encounter a MIP solution, if this thing is true, then you will implement, those pieces of code will be, solving the NLP problem, then you add a cut corresponding to the NLP. Yeah, that will be the single tree implementation, right? But now you implemented this callback, the optimization solver is not aware of this callback function. So you need to do OPT set callback, my callback. Now the optimization solver is aware of this callback you have defined. Now when you start solving this problem, whenever it encounters a MIP solution, this function will be executed, right? Okay. Yeah, so that's a lazy constraint. And another callback is called a user cut callback. The idea is that the user may know some ways of strengthening the LP relaxation based on either the problem knowledge or some other tailored cuts for this particular problem. Although the MIP will add cutting planes, it is not aware the problem-specific knowledge, right? Especially for people working on this like vehicle routing problem or traveling salesman problem, they can derive much stronger cut than the standard cutting planes. So what they would like to do is that whenever you are at a fractional solution in your branch and bound node, they will check what are the cutting planes, additional cutting planes you can add on top of the default cutting plane provided by Groovy, right? And as you can see, if you have a user cut callback, then the CB where will not be a MIP solution, it will be a relaxation instead, right? So the MIP solution is activated when you want to add things like lazy constraint, right? When you have a MIP solution, then you check whether it violates the OA cut or software elimination cut. But the user cut is added when you are at an LP relaxation of a given node. You add additional cutting planes to strengthen the LP relaxation. Okay, so that's a main difference of user cut callback and lazy callback or lazy constraint callback. Okay. So the key takeaway here is that lazy constraints are necessary for you to get the optimal solution or the feasible solution, right? Because the lazy constraints are part of the constraints for the original model. You have to have those software elimination constraints in order to be a valid TSP tool, right? So those are necessary, but user cuts are not necessary, right? If you, let's say, if you don't add any Montgomery cuts, your branch and bound still converges, right? You can think about the user cuts as another type of cutting planes to help you strengthen the LP relaxation, right? Okay, so how to implement that? You can take a look at these callback codes, especially the where, right? So this will give you what this CB where comment, CB where object can be. Right, you can activate the callback at a MIP solution, right? Whenever you find a new MIP incumbent, it will activate the callback. Or you can, let's say, currently simplex barrier. Yeah, so the MIP node should be the where value you are going to use when you want to add a user cut callback, right? When you are currently exploring a MIP node. Yeah, of course, I just talked about it for a couple of minutes. In order to use that, you need to get your hands dirty and try some problems to use those callbacks. Okay. Let's see, any questions related to this? Maybe too confusing. Yeah, you have to use those callbacks in order to get a better understanding. I would suggest, I mean, running this piece of code, then you have a better understanding of how it works. Yeah, so the most important thing I want to talk about today is how to read the log file of the solver, right? My point is that don't treat the solver as a black box, right? Sometimes when the model doesn't solve, it might not be the solver's mistakes, it could be your mistakes sometimes, right? So you do want to read carefully about the solver log. That's why I put this in bold, is that whenever you solve a non-trivial optimization model, read very carefully the log file of the solver. So let me go through a sample log file and show you how to read that. Can people see the font clearly? Is it clear? Well, okay. Yeah, so first of all, it will show you what type of hardware you are using to solve this model. It is a 48-core processor. Usually, if you have 48 physical cores, it will show it has 96 threads. But if I set the threads number to 8, it is using only up to 8 threads. Okay. And whenever you solve a model, it will first tell you what is the size of this model. It is optimizing a model with around 92K rows. The rows are the constraint, the columns are the variables, right? The 50K columns. And variable types, there are some continuous variables, some integer variables, and all the integer variables are binary variables, right? So here is where you want to check very carefully whether you are making some mistakes in your formulation. This is a matrix range. Okay, so here it says my matrix range, this is a left-hand side matrix of an MLP, right? Is from 10 raised to the power of -2 and 5 times 10 raised to the power of 2. So it's like 0.01 to 500, right? So that means the matrix is in the right range. Typically, if your range is over 10 raised to the power of 5, then you might want to scale your problem, right? This is due to the numerical linear algebra. When you take a matrix inverse and your range is super large, then the matrix is U condition, right? That means you have a very bad scaling of the parameters in your model. Definitely, you want to change, your formulation a little bit, or your parameter scale a little bit, right? Again, my point is that don't treat the solver as a black box. You should be able to understand what's happening underneath the hood at the linear algebra level. Right? It's not even at the simplex level. You should understand, what you are doing with the pivoting simplex, right? Basically, you are doing some matrix operations, right? At least doing some matrix inverse in the first round. Whenever you take a matrix inverse, you care about things like condition number of the matrix and so forth, right? So definitely, if you have a large range, you want to make some changes. And the objective range and the right-hand side range will affect the right-hand side parameter of your problem. That is not as significant as the matrix range, but you still don't want to make them too large. Here, for example, my right-hand side range is a little bit too large. It's 10 raised to the power of 8. So you must have some parameters on the right-hand side that is super large. Perhaps you set a very large big M value there, right? So then remember that choose those big M values very nicely. You want to minimize the big M values and so forth, right? And now it says I find a heuristic solution of this. That means the solver is executing some heuristic routines to find a feasible solution. And then here's where pre-solve comes into play. So pre-solve can be pretty fast, right? It removes a significant number of constraint and variables after pre-solve, right? Remember originally I have 92,000 constraints, but pre-solve already removed 83,000 constraints, all right? The majority of the constraints are already removed by pre-solve. Okay, after the pre-solve, you are left with only a few thousand variables and constraints, okay? Yeah, so now it will start solving the relaxation. Here, I didn't change the LP method of the solver. It will try to decide what type of linear programming algorithm it should use. For example, here it decides to use barrier, right? Okay. So here it uses barrier. So that's all the barrier iterations. You can check the primal objective, the dual objective. At the end of the day, the primal and dual objective should converge, right? And the other columns are the primal and dual residuals. As you go to termination, the residuals should converge to 0, right? So here, as you can see, barrier can solve this linear programming problem pretty fast. It gives you the objective here. But as I said, it must have done some crossover to give you an extreme point solution. Okay, so let's suppose it has already done that. Then it will start doing branch and bound, right? This column specify the number of explored nodes and the number of unexplored nodes, right? At the root node, it just assume I'm still processing the root node. The number of explored and unexplored node are 0 and 0, right? And at the current node, it will give you the current node's objective function. What is more important is the best bound I've found so far, right? So this is the best bound I've found so far, and this is the best incumbent solution here. Okay, so I guess in this problem, I'm actually maximizing. This is the bound, this is the incumbent solution here. And we'll calculate optimality gap, right? And here there is a letter H. Here, right? What does H mean? Means that the heuristic have find you another feasible solution, right? As you can see, when this H appears, the incumbent solution improved here, right? And then there's another H here, as you can see, after the H occurs, the best incumbent solution improved. Okay, so the solver will spend a lot of time on the root node, right? As you can see, you scroll down until this line. I'm still at the root node for 8 seconds, right? So at the root node, what the solver does is that it will keep adding cutting planes and keep running the heuristic to say if you can find a better bound and better solution, right? Then after the root node, it will start doing branch and bound, right? And typically what I usually want to check is that what is the bound of the LP relaxation, right? So the original LP relaxation is 1.77 times 10 raised to the power of 4, right? So that's what the LP relaxation gives you without adding any cutting planes, right? Then if you compare the LP relaxation with the last line at the root node, is 176 something, right? That is the effect of adding cutting planes, right? Otherwise, you are not going to tighten your LP relaxation. So as you can see here for this problem, adding cutting planes does not seem to be so effective, right? It is 1.77, this is 1.76, right? So adding some cutting planes doesn't help you reduce the bound that much, but for some of the problem, it can be very significant, okay? Yeah, and the heuristic, of course, the heuristic keeps improving the best known solution so far, right? And then after processing the root node, the solver will start doing the branch and bound. As you can see, the number of explored nodes and the number of unexplored nodes keep increasing. Okay, and at the end of the day, it uses around 70,000 nodes to find the optimal solution. Okay, and here it tells you what are the cutting planes added to this problem, right? And it says that these are the number of nodes explored, and these are the total number of simplex iterations, right? And here the simplex iteration are mainly dual simplex iteration, right? You use dual simplex to warm start the LP solve, right? As you can see here, at the beginning, the solver was using barrier algorithm to solve the root node relaxation. But once it starts doing branch and bound, it will use simplex, right? That's the dual simplex algorithm it uses. And here it found 10 different solutions while doing the branch and bound. So you can retrieve these 10 solutions even if you don't add additional aggressiveness to the solution pool. If you want more solutions, you are going to change the solution pool parameters.
First three are the same.
The first three are yeah, so that should give you different solutions that give you the same objective. I mean, this problem can be degenerate. Yeah. Okay. So then it will tell you what are the best objective, what are the best bound. Okay. Yeah. So let's go back to my slides. Here's some of the key properties you should check once you solve an MILP model. First, make sure you check the matrix range and right-hand side range to see if you have some very odd number showing up. That must mean you have made some mistakes in your modeling. Although the solver can solve the problem, maybe the solver is very well engineered. It helps you fix the problem, right? Right. You do want to check it very carefully. And then check the root node relaxation and check the root node bound after adding the cutting plane. This will give you an idea of how effective the cutting plane is. An easy problem usually can be solved pretty fast without doing much branch and bound. And for hard problem, as you can imagine, branch and bound can take exponential number of nodes, right? So there will be a very large memory consumption. So for people doing research on combinatorial optimization, typically you need to get a server that has a large memory. Right? For example, I got a server with 1 terabyte memory. If you go to the Purdue Rec Center, they only sell servers with 128 gigabytes of memory. That wouldn't work for most of the large-scale combinatorial problems. Right? So you need to think about what hardware you need as well when you are running those type of experiments. And be careful about the memory usage. Sometimes you run out of memory, and then what the server will do, it will start saving the branch and bound nodes to the hard drive, right? So that will slow down everything. So make sure if you are running large scale problem, do check your process, let's say every couple hours, such that you don't use all the memory, right? And if you congested the server with large memory usage, it's even very hard to shut down the server when you have so much memory, okay? And then you should diagnose why this model is so slow to solve. Of course, in optimization, there are two things that make the problems hard to solve. One is finding good feasible solution. The other challenge is closing the gap, right? Typically, the second challenge is much harder than the first challenge. When you want to close the gap, it will do a lot of branch and bound to close the gap, right? So that's also the main difference between global optimization algorithm and some heuristics, right? If you do genetic algorithm, you don't care about how far the solution is from the global optimality. If you want to certify global optimality, it's generally much harder than finding good feasible solutions. Okay. And here I forgot to mention one thing. You should also check what are the bounds of the optimal solution compared with the root node relaxation, right? Here the root node relaxation is 176, and at the end I got 128, right? So the root relaxation gap is around, let's say, 30% or so. Right. So this is not such a trivial problem. Usually the higher quality the LP relaxation is, the easier the problem is to solve. Right. And for harder problem, you could have a very large gap. Okay. Yeah. So then I think that's pretty much I want to talk about. Here are some of the references. I especially recommend the CPLEX user manual if your research area is in optimization. This is a very good bedtime reading. It doesn't go to the details of the math, but it will tell you what's within the the box of Cplex. Okay, and the Groovy documentation is less comprehensive than the Cplex user manual. The other thing is this Groovy YouTube channel. Okay, definitely follow this YouTube channel if you work on this area. Every year they will release, for example, definitely watch this video, what's new in the new version of the solver. Like every year around October, they will release a new version. Okay, so definitely, I would recommend watch this this type of release videos. Okay. Yeah, and then if you want to know how to add user cards versus lazy constraint, there is a gentleman whose name is Paul Rubin, who wrote a very nice blog on what are the difference between the